Working on 12-3, double integrals in polar coordinates. Starting out here with number 5, we're asked to sketch the region and then evaluate this integral. So taking a look at this, let's try and come up with what the restrictions on theta and r are. So theta is the outside variable, so my theta is stuck between pi over 4 and 3 pi over 4. And then our radius, which is the inner integral, is stuck between 1 and 2. So in a polar region, what this looks like is all points that are within an angle of pi over 4. So here's pi over 4, 3 pi over 4, which is over here. So it's all points in this region that have a radius between 1 and 2. So let's say that this is 1. No, you know what, let's make this 1, and that's 2. Then if we go out 1 up here, imagine having a circle radius 1, and then a circle radius 2, like this. Then we want all the points between these two angles and between these two radii. So this is our polar region right in there. And then to evaluate this, we're going to do the inner integral first. So we're going to take the antiderivative of r with respect to r, which is 1/2 r squared. We're evaluating that from r equals 1 to 2. And then we'll integrate that with respect to theta. So you plug in 2 here, you get 4. Half of 4 is 2. And then you plug in 1, you get 1/2. So you're going to do 4 minus 1/2. So integral from pi over 4 to 3 pi over 4 of 4 minus 1/2, which is 7/2 d theta. The antiderivative of 7/2 with respect to theta is just 7/2 theta evaluated pi over 4 to 3 pi over 4. So you plug in 3 pi over 4 here, you get 21 pi over 8. I'm going to do that right here. 21 pi over 8 minus, now plug in pi over 4, you get 7 pi over 8, which gives you 14, I forgot the pi here. This gives you 14 pi over 8, which is just 7 pi over 4. Something ain't right. What did I do wrong? 3, 21, 14, 25, 8, 7. Let's see, 4. Oh, I said 4. Darn it. I said, should I start the whole video over? No, I shouldn't start the whole video over. I said 4 minus 1/2. I don't know why I said 4 minus 1/2. Let me go back to this. Okay, plug in 2 here, you get 4. Half of 4 is 2. 2 minus 1/2, 3/2. It's my first problem of the day. Give me a break. This is 3. And then now plug in, you get 9 pi over 8 minus 3 pi over 8, which is 6 pi over 8, which is 3 pi over 4. Okay, sorry about that. All right, number 7. So number 7 is the first one where we actually have to take something and convert it over to polar coordinates. So let's take a look at the double integral. We want the double integral over the region D of x squared y dA, where D is the top half of the disk with the center at the origin and radius 5. Top half of a disk centered at the origin, radius 5. So we want that region right there. So to convert this over to polar, our angle is going to go between 0 and pi. So theta is going to be between 0 and pi. And the radius is going to be between 0 and 5. And then I'm going to take this over here and convert this function of x and y over to a function of r and theta. So remember, all my x's get replaced with r cosine theta. All my y's get replaced with r sine theta. So this double integral becomes, because I'm going to polar, my little dA turns into r dr d theta. Since theta is my outside integral, I'm going to go 0 to pi here. R is the inner one, so 0 to 5 here. And then x squared becomes r cosine theta squared, so I'm going to square the r and square the cosine. And then y, which is r sine theta. And then I can put this all together, combine things together, go from 0 to pi, 0 to 5, and then I have r squared, r, and r, so that's r to the 4th. I'll do sine theta, cosine squared theta, it doesn't matter what order I put those in. Dr d theta, like that. And now I go about integrating this. Notice that I could split my integrand up because I have r's by themselves separated by multiplication, and then I have theta. So I could do two separate ones, or I could just do the integration. Let me just do the integration without splitting. You get the same answer. So outer integral 0 to pi, and then antiderivative of r to the 4th sine theta cosine squared theta with respect to r is just 1/5 r to the 5th, and then I still have the sine theta cosine squared theta. Evaluating that from r equals 0 to 1. Oh, that's nice. D theta. When I plug in 1, I just get 1/5 times this. When I plug in 0, it zeroes out. So I should just be left with 1/5 sine theta cosine squared theta. I'm going to bring the 1/5 out of the integral. 0 to pi. How about I do this? Cosine squared theta, sine theta. Just reverse those. And the reason is because I'm going to do a quick u substitution on this. I noticed that if I let u be cosine theta, the derivative of that is negative sine theta d theta, which I have sine theta d theta. So I'm just going to make this a negative, make that a positive. So now they match up. So that integral over there is going to become integral u squared times negative du, so negative du. And the antiderivative of that is negative 1/3 u cubed, which is negative 1/3 cosine cubed theta. So that's what I know the antiderivative of this is. But I had 1/5 in front. So it's going to become 1/5 times negative 1/3 is negative 1/15 cosine cubed theta, evaluated from theta equals 0 to theta equals pi. And when I plug in pi, right, cosine of pi is negative 1. Negative 1 cubed is negative 1 times negative 1/15 gives me 1/15. Minus cosine of 0 is 1, cubed is 1, times negative 1/15. So I get minus negative 1/15. So those add up to be 2/15. God damn it. I just realized something here. I'm sorry I'm getting a slow start for the day. I realized on the original problem, the radius went from 0 to 5, not 0 to 1. I don't know why I put 1 in there. Oh, frustrating. This should be a 5. Why did I put 1? Well, let's do this. Because I don't want to redo the problem, and I hope that you just get the basic idea. Let's just change the problem number 7. Change it to 1 here, and then this is all correct. Okay, I'm trying to get my stuff together here, as you know what I'm saying. These are the easy problems. I'm having trouble just writing things down correctly. Jeez. All right. Number 9. Okay, Robert, get this one right. Number 9. Double integral over some region R of sine x squared plus y squared dA with respect to area. The region is the first quadrant. It's in the first quadrant. Between the circles with center at the origin radii 1 and 3. So I have a circle with radius 1. I have a circle with radius 3. I'm looking at the region between them. See, only in the first quadrant. So let's talk about our restrictions here. Theta has to be between 0 and pi over 2. And my radius has to be between 1 and 3. So I'm going to convert this to a double integral now. This is going to, a polar integral. Double integral, I know I'm going to be using r dr d theta. And then theta is my outer, so 0 to pi over 2. The inner is 1 to 3. Let's get this right. And then I replace this, and I switch all my x's and y's into, in terms of r and theta. But I remember that x squared plus y squared equals r squared. So that was one of our equations that we had that we use when we convert back and forth. So this just becomes sine of r squared. And that's it. So I get to integrate this, and that should be a pretty straightforward integration. When we do the inner integral, the antiderivative of sine of r squared times r dr, just looking at this piece right here, I notice that if I let u be r squared, the derivative of it is almost here. So what I'm doing is this. What I'm doing is I'm letting u be equal to r squared, derivative of that, 2r dr. Take half on both sides, r dr. So I'm going to replace r dr with 1/2 du. I'm going to replace r squared with u. So that integral becomes integral, 1/2 comes out, sine u du. The antiderivative of sine of u is negative cosine u. Okay, so I know that the antiderivative of this in here is going to become negative 1/2 cosine of u, but u is r squared. And now I'm evaluating this from r equals, let's get this right, 1 to 3 d theta. Okay, now this becomes integral 0 to pi over 2 of, let's plug in. So when we plug in 3, we get 9. So I have negative 1/2 cosine of 9. That. And then I get, plug in 1, but I'm subtracting, so it's going to wind up adding 1/2 cosine of 1. D theta. And then from here, I integrate with respect to theta. These are just constants. So the antiderivative of this with respect to theta is this times theta. Antiderivative of this with respect to theta is this times theta. Or you can say the whole thing is a constant. The antiderivative of the whole thing, right, is with respect to theta is the whole thing times theta. That's the way I think I'm going to do it. So this is negative 1/2 cosine 9 plus 1/2 cosine 1 theta, and then evaluated theta equals 0 to pi over 4. And when I plug in pi over 4, I just get pi over 4 times that. When I plug in 0, it wipes out. So my answer is going to be weird looking. Negative 1/2 cosine 9 plus 1/2 cosine 1 times pi over 4. Whatever that is as a decimal. But we can just leave it like that. Minus on there, plus on that. Okay. Number 13. So here's where things start getting a little more interesting. For number 13, use polar coordinates to find the volume of the given solid. So I want to be find the solid volume of the solid under the cone given by the equation z equals root x squared plus y squared, and above the disk x squared plus y squared less than or equal to 4. So just FYI, if I were to try and graph this, okay, here's x, here's y, here's z. The cone, which is this guy right here, starts out at the origin 0, 0, and then goes out. I have a cone. And I'm trying to find the volume underneath this cone, but above this disk. So the disk lies on the ground, it has a radius of 2. Right? This is x squared plus y squared less than or equal to 4, so my radius squared is 4, so my radius is 2. So imagine on the ground here a disk. And what we're doing is we're going up in here and we're trying to find the volume down below the cone and above this disk. So it's going to look something like this, like my solid. It's kind of like this, but there's a cone inside, so it's kind of hollowed out on the inside, and trying to find its volume. So, all right, so the way we'll do this, our region of integration, okay, is what's on the ground there. That is that, which means theta is between 0 and 2 pi. That's all the way around. And then my radius is between 0 and 2. So I'm going to switch this over now. Also, the top function, right? The top function is this. So I could say that the top function is that one. And the bottom function, the bottom of this solid, is always going to be the ground. So my bottom function is just the 0 function. So anytime we want to find the volume between two surfaces, we do this one minus this one. So it's really just going to turn out to be that. We're taking a double integral of this. So I'm going to go double integral. I'm going to polar. Since I'm going to polar, it's going to be r dr d theta. And my restrictions here, 0 to 2 pi, 0 to 2. And then on the inside, I need to take my function of x here, minus this, which is just this. And then notice that that right there is r squared. Square root of r squared is r. So just get r right there. And this together is r squared, right? So let me do that. I'm just going to erase that r, make that r squared. So this one's pretty straightforward. So I'll just antiderivative of r squared is 1/3 r cubed. Evaluating r equals 0 to 2 d theta. Plug in 2, we get 8/3. Plug in 0, we get 0. So I'm going integral 0 to 2 pi of 8/3 d theta, which is just 8/3 theta evaluated from theta equals 0 to 2 pi. And you plug in 2 pi and you get 16 pi over 3. Plug in 0, you get 0. So we should get 16 pi over 3 is the volume of that solid. What number was this? 13? Okay. Oh wait, 15. Find the volume of a sphere of radius A. Interesting. 15. Find the volume of a sphere radius A. So we have a sphere. We'll center it at the origin. It has a radius of A. Right? We're trying to find the volume of this. I know that the equation of this sphere is x squared plus y squared plus z squared equals a squared. We learned that like on the first day of class. And if I want to look at this, try and find this volume, what I could do is like cut the bottom of the sphere off, right? And just look at the top half, take that answer and double it. So if I do that, the top half, the top cap of this sphere, I can get from this equation. I can get the function of x and y that gives me the top cap. And to do that, I just solve that for z. So I get square root a squared minus x squared minus y squared. And then the bottom of this, so I'm just looking at the top hemisphere. Right, so the top cap is this. The bottom cap is the g function, that's just 0 again. And I need my region of integration. My region of integration is going to be the ground here. And so that I should be able to get pretty easily. I can do that here. It's just a circle radius A. So my theta is between 0 and 2 pi. And my r is between 0 and A. Okay, double integral time. Doing the double integral, I'm in polar coordinates, so r dr d theta. Theta goes from 0 to 2 pi. Radius goes from 0 to A. And then I'm doing this function minus this function, which is just this. I recognize that that right there, I can pull out a negative. And that would give me minus r squared. So this is a squared minus r squared under a root times r dr d theta. That should be a pretty straightforward integration. If I integrate this with respect to r, let me do that over here. If I integrate, I'm just doing the integration over here just so you can see it. If I let u be equal to a squared minus r squared, the derivative of that is negative 2r dr, and negative 1/2 du is r dr. So I'm going to replace that with negative 1/2 du. This will become the square root of u. So this integral becomes negative 1/2 integral of square root of u, which is the same as u to the half du. Antiderivative of u to the half is going to be 2/3 u to the 3/2, but then I had a negative 1/2 outside. Twos cancel, I get negative 1/3 u but u was a squared minus r squared to the 3/2. So the antiderivative of this right here with respect to r should be this. Let's go ahead and write that down. So this equals integral 0 to pi, okay, -1/3 a squared minus r squared to the 3/2, evaluated from r equals 0 to a. And then whenever I figure out what that is, I'll integrate that with respect to theta. So let's plug in r equals a first. If r gets replaced with a, this is a squared minus a squared is 0, that's all gone. If I replace r with 0, I get a squared to this power times -1/3. But remember, I'm subtracting, right? So it'll become plus, watch. When I plugged in this, I got 0. Minus, when I plug in this, I get -1/3, a squared to the 3/2. Yeah, that's it, d theta. So that what I was saying is that the minus becomes a plus here. So this becomes integral 0 to pi of +1/3 a, oh, what happens here, we multiply these two powers, we just get a cubed. That's nice, d theta. Now I'm integrating this with respect to theta. A is a constant, this whole thing is a constant, so the antiderivative is just 1/3 a cubed theta, evaluated from 0 to 2 pi. Plug in 2 pi, we get something, plug in this, we get 0. So we should just get 2 pi over 3, so that's what I get when I put this here and over the 3, a cubed. And that's it. That's the volume of the upper hemisphere, just the top half. So if I double this answer, I get the radius of the sphere. So to answer this question, I take that, multiply by 2, I get 4 pi over 3 times a cubed. All right, that's number 15. I'm not going to do 16. But I think you should try 16, it's kind of cool. How about number, let me see, 17. I think 17 is, well, I want to leave you to do some of these. Let me do 17, and then I think I'll leave you to do 19 on your own. They're similar. 17, find the volume of the solid that is above the cone z equals square root of x squared plus y squared. They like that one. And below sphere x squared plus y squared plus z squared equals 1. Wait a minute, did I do this in class? This looks like one I did in class. Yeah, I did that one in class. Okay, well, then I don't need to do it. How about we do 19 then instead? Inside the cylinder, x squared plus y squared equals 4. And inside both the cylinder there and the ellipsoid, x squared plus 4y squared plus z squared equals 64. Let me try and draw this. Cylinder x squared plus y squared equals 4 is a cylinder with radius 2. Okay, so there's your cylinder, opens up the z-axis. I need the volume that's inside that and also inside this ellipsoid. So let me try and figure out. We know the ellipsoid looks like an egg, pretty much. Like that. If x and y are 0, z squared is 64, which means z is positive and negative 8. So I know that it hits up here at a point 8 and down here at the bottom, negative 8. And then as far as the outsides are concerned, let's figure out where it hits on the x-axis. If I zero these two out, divide by both sides by 4, I get 16, right? 4x squared equals 64 means x squared is 16, and take square root of both sides, I get 4 and 4. So 4 and negative 4, so hits here at 4, and on the back side over here at negative 4. So what I know is that the ellipsoid comes outside, okay, at 4, negative 4. I know that the ellipsoid comes outside over here. So the ellipsoid goes something like this. Up here at 8, you know, something like that. Terrible drawing, but yeah, that's pretty much it. So I'm trying to find the volume of the solid that's inside both. So you got to be inside the cylinder, but you also have to be inside the ellipsoid. So really all the ellipsoid is doing is cutting off the top of the cylinder and the bottom of the cylinder with these curved surfaces. So I get something, like my solid looks something like this. Something like that. You know, three-dimensional. You know, it's kind of a round cap on the top of it, and a round cap on the bottom. Oh, did I say cap? Okay, well, that's how we approach these things, right? What we need to do is find, for our solid, like an upper bound, an upper cap, and a lower cap. What I'm going to do is what we've done in the past. I'm going to go halfway, which would be the ground, and then to the here, and then I'll double my answer. So how about we do this? Let's figure out what the top cap is. The top cap is the ellipsoid, so I have to solve this for z. So that'll be z is equal to square root 64 minus 4x squared minus 4y squared. You know what, I'm going to call this f of xy. That's my top piece. My g of xy, which is the bottom, is 0. And then remember, we're going to double the answer. I think I'll double it right off the bat. And then the region of integration, okay, is just this ground piece, which is just that part inside the cylinder. So that has as polar, you see, a radius of 2, right? So theta is between 0 and 2 pi, and the radius is between 0 and 2. So I can go to a double integral. I'm going to polar RD theta. I'm doubling my answer because right now I'm only finding the top half, so I have to double it to get the bottom half. And then I'm doing this minus this, but I'm going to do a polar substitution here. Notice here that I could rewrite this as negative 4 factored out x squared plus y squared, just for these two. And that would give me r squared here. So this is really square root of 64 minus 4r squared. Okay, so I'm going to put that right here. Square root 64 minus 4r squared times rd theta. And my limits of integration, 0 to 2 pi, 0 to 2. I think I'll let you take that the rest of the way. Why do they have a 4 there? Oh, okay, I see what they did. All right. Yeah, no, this is good. You could factor a 4 out of both of these and then pull a 2 out and pop the 2 out here. You could, or you could just leave it as is. This integral is pretty simple to do. Make that your u, the derivative of it's out here, kind of, you have to scale, and then it's very similar to the problem I did before. That's the most important thing. There's your setup. All right, let's see if I can do number 23. Evaluate the integral converting to polar. Okay, so for this one, they give you a double integral in Cartesian. They want you to go to polar. So they're not describing the region. They're just giving you the double integral. So we have to do a little bit of investigation to get the polar region. -3 to 3. 0 to square root of 9 minus x squared of sine x squared plus y squared dy dx. So that's what we're trying to find. But we want to convert this to polar. So I'm first going to talk about this region right here. The region is created by our restrictions on y and x. Right now I know x has to be between -3 and 3, and my y values have to be between 0 and square root 9 minus x squared. So x between 3 and -3, that's pretty obvious what that is. You know, vertical lines here, all the points in here, but my y values have to be, see, my x's have to be between here. My y values have to be between 0, which is the x-axis, and this. So what I'm going to do is I'm just going to, you know, what if we set y equal to that? Can we determine what this looks like? Well, square both sides, move x squared to the left, and we realize that that really is just the top half of the circle, centered at the origin, radius 3. So that is circle. That's supposed to hit right there at 3. So we convert this to a polar region instead. Then our theta is between 0 and 0 and pi, and our radius is between 0 and 3. And then we convert the double integral over from Cartesian to polar. So we know we've got, this now becomes 0 to pi, 0 to 3. We know we can go sine of x squared plus y squared is r squared. And then we know it's always r d theta. And notice I did pay attention. Thetas are on the outside, r's on the inside. And number is this 23? Yeah, I'll just let you take that the rest of the way. We did one very, very similar to that. Okay, I think that's it for this homework for 12-3.